So Matthieu will talk about universes.
All right. Enhancing Rocq's universe level polymorphism in Rocq algebraic universes, consistency checking, and variance inference, if I can, in 15 minutes. Last time I did 1 hour and a half. So, universe levels in Rocq, typing and elaboration. You know everything about universes. If you don't have them, your theory is inconsistent. You get Girard's paradox, Herkens, whatever. You have a well-founded hierarchy indexed by natural numbers. Dependent products take the max, and usually you have a bottom universe, which we will call U0. It's predicative set in Rocq. The algebra of universes, you have variables, a bottom, successor universe, and the supremum, which is written like this in Agda parlance. We tend to write it like this in the syntax of Rocq. The theory is that 0 is neutral for max, successor distributes on max, max is idempotent, associative, commutative, and subsumptive, meaning that if you take the max of u and u plus 1, you get u plus 1. And universe polymorphism is pre-next universal quantification on universe variables. Pretty straightforward. Now, you have, of course, unification in the proof assistant. What happens? Well, Thiago found out in his PhD that the theory for this equational theory of universes is not unitary. You don't have MGUs in that theory, and the example is quite simple. You take 3 meta variables, and you have this constraint, x plus 1 is the max of y and z, and there are incomparable solutions. None is the most general for this. What it means in practice is that in Agda-Orlin, you will get stuck constraints requiring user annotations. We don't like annotations that much for universes in Rocq, especially because we also have a richer system with a cumulative hierarchy of universes where UI is included in UI plus 1, and it goes on the right of dependent products. So with polymorphism and constraints, you get bounded quantification on universe variables, which was introduced by Harper and Pollack quite some time ago, and that we refreshed for Rocq in the 2010s with Nicolas. What it means is that you can quantify on universes plus constraints, and the body of your definition should check according to this, under the assumptions of this constraint. So a priori, the consistency check you must do for universe polymorphic definitions is of this kind. You get a bunch of less than or equal constraints on universes, and you must check if some constraint is satisfiable under this, or implied by this. And then you can encode, as usual, equality by the conjunction of inequality in the 2 directions. Except it's not really like this that it was implemented, because it was really hard to handle the constraints of this form. So Hugo carefully looked at the way we can do type inference in CIC and found out that we actually only need to handle the green kind of constraints here. So constraints where you get arbitrary universe expressions on the left of the less than or equal sign, but only levels or the 0 level on the right. And you can actually enforce this invariant in type inference. And this actually means that no algebraic universe, so things that are not in the subset of just variables and 0, can appear in the term. What happens? Well, you have some limitations, and when you are trying to do some elaborations, you will need to be careful. For example, if I elaborate the identity function, I'm not giving the first argument, which is the type of the object I'm taking the identity of. I put type 0 there. So my meta variable x has type at id of .u0, which is the global universe for the identity function universe. You type check, and then you find that you have a cumulativity constraint that instance of x must be greater or equal than type 1. Well, you can't instantiate x with type 1 because this is an algebraic expression. It's not type 0 or type L for a level. So what you do is that you just leave the constraint and leave this universe variable. And this is okay because you only have constraints in the subsets that we were mentioning. So the pro of this solution is that you have efficient satisfiability and validity checking. This was improved even by Jacques-Henri Jourdan, who implemented a state-of-the-art algorithm from Bender and Targin in about 10, 15 years ago already. And at the time, we saw a 30% time improvement in checking. The cons is that you have this restricted algebra. The API is very error prone. You must remember to refresh the things that you get from typing to not put them in terms if they contain algebraic things. This results in a proliferation of fresh levels and constraints, especially to avoid this forbidden constraints. What happens if you add polymorphism? Just the same. This adds a constraint that instances of universe polymorphic definitions must also only contain things that are non-algebraic. So you get the same kind of stuff, even with more fresh levels and more proliferation of constraints. Let's solve that problem. Using, as frequent in the type theory literature, an idea from Thierry that he worked on with Marc Bezem. So they propose a new algorithm to solve the loop checking and uniform word problem for joint semi-lattices with an inflationary endomorphism. And what it means is that satisfiability is decidable for this max plus and less than or equal algebra in any semi-lattice, actually. It's actually a well-known problem. If you restrict the problem to increments in Z and solutions in Z as well, it's called the Manhattan problem, which lives in NP intersection co-NP, which is an interesting class, for which usually we have polynomial solutions, strongly polynomial solutions, but in this case we don't know if there is one. Weakly polynomial means it's the solutions are, the complexity is proportional to the magnitude of the increment. So if you have a problem with very large integers, you will get slow, but if you have just plus ones and plus twos, like we do for universe checking, it's not going to matter much. How does it work? We have basically a kind of logic programming forward search on a set of round clauses. So we are translating this constraint into clauses of this form. So you have a single universe here, maybe with an increment, but not a max. And on the left, you can have max. So exactly the kind of hard constraint with max on the left, max on the right, sorry, like this one. So here I'm building a very simple graph, and the idea is that we maintain some kind of minimal model of these clauses in the integers plus infinity, where infinity will represent a looping universe, basically. So the lowest universe will have highest value. So you see here S is the smallest universe, and it gets value 2. And W is at level 1. It's just one level higher, and so on and so forth. Okay. I'm not going to go into the details of this algorithm. I'm just going to tell you that I proved it correct in Rocq. I had to extract the proof from Thierry's and Marc's paper, because I had a constructive proof on paper. It was constructive, indeed, yes, but it was really not even an algorithm. So we have an incremental version of this algorithm. So as soon as we find a loop, we don't care about the rest of the valuation. We just report a loop. We support an injective morphism, where there's just an inflationary morphism, so not assuming injectivity. And it's implemented as two quite complicated, nested, well-founded recursive definitions. It's sound and complete for the initial semi-lattice, so Z infinity max and less than or equal. And if you use the fact that Z has a total order, it's also sound and complete for satisfiability and validity in this algebra. So you can think of your universes as before in Z or in NAT. I mean, all our universes are greater than 0, so it's easy to say, to see it as an algorithm for natural numbers as well. Okay. So it provides a pretty simple model for working with universes. You have an interface where just you're manipulating just a universe model, which always has 0 declared. It contains only this universe. Then you have a function to push some set of universes and constraints. And it's going to tell you, oh, there is a loop, or I can find a model. And then you have a way to check if some constraints are implied by some universe model. And it's reflective, so it can actually run in Rocq, and we use that in MetaRocq. Okay. So now for the implementation in Rocq itself, in OCaml, it's pretty direct translation. It's a functional program. We have some optimizations that are inspired by the previous algorithm to have a more efficient representation of the equivalence class of your universe levels. So a kind of union find structure. It greatly improves the API of Rocq. I can remove the refresh universes function. It's great. I love it. Universes can appear anywhere, so it's closer to Agda and Lin also. And we have a general substitution operation on these models that allow us to do instantiation of universes during elaboration, which is also useful. So still there is a problem with universe polymorphism and cumulativity, is that when we do elaboration, we have a large number of unnecessary constraints and universes that are generated. If I'm going back to the identity, I apply it to type at 0 and nat. Then I get a constraint that I must be greater than 1 rather than an equality between them, which you would get in a non-cumulative system. But at the same time, without loss of generality, we could assign 1 to I without losing anything. The principal type of the expression will be the same, and even the conversion behavior of the expression will be the same, because however you instantiate this universe variable, the normal form of the identity goes down to nat. So we're going to record how and where universes appear to perform this kind of simplifications when they're really not losing any generality. So the idea is to maintain some information about the variance of universes, how they appear in terms. You can have irrelevant, covariant, contravariant, or invariant. And actually, that's an idea that was already present in our work on cumulative inductive types with Amin Timani, where here for the equality type, we can say that I, the universe binder, is irrelevant, as soon as EQ is applied to at least one parameter. The analysis is a bit more complicated than that, but I cannot go through it. But basically, the idea is that we can have soundly the rule that EQ at I of nat and 0 and 1 is always equivalent to EQ at j of 0 and 1, living in the maximum of these two levels. And it's also the kind of the idea behind the template polymorphic universes. And the idea here will be to just leave this analysis to all definitions. For example, if you take the definition of relation, takes a universe and a type in this universe, you can look at the way it can be unfolded. You'll find out that this universe is also irrelevant as soon as relation is applied to at least A. So this enables us to do a sound first-order unification rule, and a faster one, because we don't need to compare irrelevant universes. And it enables also minimization of these universes. And this is compositional, so from relation you can look at proper, respectful, all the definitions of set writing. Basically, you only have irrelevant universes. Same for containers, as you would expect. Things that use their types in a parametric way, the universe attached to their type is going to be used irrelevantly most of the time. Finally, we have two modes to work with these universes when we are writing lemmas or definitions. You can do a kind of mixed inference mode where you bind the universes that you want to quantify on explicitly in your definition, and then the minimization will solve for these universes. So it will try as much as it can without losing generality to find a solution in terms of I and j, and it will tell you otherwise that some universes cannot be simplified. Or you can be in full checking mode where you control exactly what constraints and universes are allowed. That's it for me, I think.
One quick question for Matthieu. And could the next speaker come forward?
Cool. I was wondering, how does the whole model theoretic algorithm work with unification? Is it an easy extension? Do you have to do something complicated there to handle universe level meta variables?
No, they're just treated like variables. because you can express equality and less than on variables, and you don't need more than.
Okay.
It's important to have the instantiation function so that you can instantiate the meta variable, but otherwise it's
Nice.
simple.
You said something that worried me. You said, as soon as we have a loop, we don't care.
We report the loop. I said we report the loop, and we don't care about the valuation of the other levels, because we can tell the user there's a universe for which you have I plus 1 is greater than I is greater than I plus 1.
So you can have very good information about where the problem is.
Yes, it's not producing minimal loops by default, but you can find them if needed.
I think we need to move forward, but let's thank Matthieu again.